The AQA spec for halogenoalkanes. The first thing it says on the spec over here is that halogenoalkanes contain polar bonds. We know that halogenoalkane is an alkane with at least one halogen atom in place of a hydrogen atom. So let's draw the molecule bromopropane, for example. Bromopropane to one bromopropane, I should say, actually. So this molecule is polar because we know that the halogens are more electronegative than the carbon atoms. Electronegativity is the ability of an atom to withdraw electron density from within a covalent bond. So that might sound like a lot, but it just means that the bromine pulls the electron towards it. So we know we have in covalent bonds, lone pairs are shared between two elements or two non-metals more precisely. But in this case, because the bromine is more electronegative than the carbon atom, it actually pulls the electron density towards it. And that results in the bromine being a delta negative, so a partially negative atom, and the carbon is therefore partially positive because it is electron deficient, and this is electron rich. So the bromine is electron rich, which is why it's negative, because we know that electrons are negative subatomic particles. So now we know why halogenoalkanes contain polar bonds. Let's go on to what nucleophiles are. So a nucleophile is an electron pair donor. They usually have one or more lone pairs of electrons on them, like ammonia, for example, has one spare pair of electrons. This lone pair of electrons on the ammonia and other nucleophiles are attracted to the partially positive atoms like carbon because they are electron deficient. That's why halogenoalkanes are susceptible to nucleophilic substitution, is because they're polar molecules. So the next point on the specification is that halogenoalkanes undergo substitution reactions with the nucleophiles hydroxide, cyanide, and ammonia. It says students should be able to outline the nucleophilic substitution mechanisms of these reactions. First one, halogenoalkanes react with hydroxides like aqueous sodium hydroxide or potassium hydroxide to make alcohols. So let's draw our halogenoalkane over here. This is going to be bromoethane, and we can draw the partial charges. We don't need to draw the partial charges, but while you're learning it, it's better to have them on there, just so you remember, just to remind you of the fact that the molecules are polar molecules. So we know in aqueous conditions, salts like sodium hydroxide and potassium hydroxide, because they're ionic salts, they will dissolve and we'll just get the hydroxide nucleophile. The hydroxide nucleophile has a lone pair of electrons on them, and the delta positive carbon attracts the lone pair of electrons. So the hydroxide nucleophile attacks the carbon atom and breaks the carbon-bromine bond, and this results in us getting ethanol as our product. And we get, so a key thing to remember is that this only happens in aqueous conditions, and it has to be these salts, and another condition is that it's warm. So the next substitution it asks us to go through is the cyanide ion with halogenoalkane. When you react ethanolic potassium cyanide with a halogenoalkane, you get a nitrile. So the mechanism for the reaction looks something like this. So let's come up with a molecule we'll use 1 bromopropane. So let's just draw the delta positive and the delta minus. So you have a delta positive carbon and a partially negative bromine, and we have our cyanide nucleophile. I'll draw the electrons in red. So the positively charged carbon will attract the lone pair of electrons, and subsequently the cyanide ion will attack the carbon atom, and then the carbon-bromine bond will break, and we will get resulting butane nitrile. And of course, a bromide ion. So the conditions for this reaction is that it's ethanolic potassium cyanide, and another one we could say is that it's warmed and it's refluxed. But these are less important than these, and then it being ethanolic and potassium cyanide. Some exam questions like to use hydrogen cyanide. Although hydrogen cyanide will work, the key points to remember is that hydrogen cyanide dissociates less readily into the cyanide ion than potassium cyanide dissociates into the cyanide ion. And of course, when you react hydrogen cyanide with a halogenoalkane, you get a very toxic hydrogen halide gas. Let's say, for example, you're reacting with chloromethane, you'll get hydrogen chloride gas, which is very toxic, which is why it's often avoided in industry. So that's just a side note to remember when you're answering exam questions. Last but not least, it asked us to go through the reaction with ammonia. So when you warm excess ethanolic ammonia with a halogenoalkane, you get a molecule called an amine. Choose a simple molecule now like bromoethane, and we will draw the delta positive and the delta negative charges in. And our ammonia molecule, it has a lone pair on it. And of course, as mentioned previously, the carbon atom is positively charged and it attracts the lone pair from the ammonia to it, and the carbon-bromine bond is broken. This results in us getting this molecule with the nitrogen bonded to 4 different atoms. And when this happens, the nitrogen actually gets a permanent positive charge. Because of that, the electrons within one of the bonds between the nitrogen and hydrogen attacks the positively charged nitrogen, and it actually breaks off. So we get an amine, which is going to be ethylamine, because we have 2 carbons, so we get the eth, and then the ylamine comes from the NH2 group over here. It's important to remember that this is still a nucleophile in itself, because the nitrogen has a lone pair of electrons because it's bonded to 3 other atoms. So this could go through other reactions known as further substitution reactions, which you shouldn't worry about right now, and it's something that you'll cover later within the syllabus. So the side products of this reaction will be our bromine, our bromide ion. We'll have a hydrogen atom, and because this reaction occurs in the presence of excess ethanolic NH3, we have NH3 ammonia, and the ammonia reacts with the hydrogen and it forms a dative covalent bond, which you might have learned about before, and we actually get ammonia, NH4 plus. And often in questions like this, you'll see the product of a side product of them is often something like this, so ammonium bromide salt, because we get the NH4 from the excess ammonia and one hydrogen proton from the nucleophilic substitution, and of course the bromine which gets kicked out. And of course this is the ionic salt, because the NH4 is positively charged and the bromine is negatively charged. You can actually write it like this: NH4 with the positive charge and the Br minus, to show that it's actually an ionic bond. So the conditions for us to get an amine are excess and ethanolic ammonia. We can also say warm, but that is less relevant than these 2 main conditions: excess ammonia and ethanolic conditions. So now we've gone through all of the different mechanisms. Let's look at the final spec point, and it says explain why the carbon halogen bond enthalpy influences the rate of reaction. So if you look at group 7, the halogens actually get bigger as we go down the group. They increase in size, the atomic radius increases. When we look at the strength of the carbon halogen bond, we notice that they actually decrease down the group. This is because the smaller the atom is, the closer the nucleus is to the shared pair of electrons within the covalent bond. So because fluorine is smaller than iodine, the covalent bond that fluorine has with the carbon, the nucleus of it is closer to the shared pair of electrons within the covalent bond. This means that more energy is required to break that bond because it's stronger, and it has a higher bond enthalpy. So the carbon-fluorine bond actually has the highest bond enthalpy, and this actually has the lowest bond enthalpy. So bond enthalpy is the energy required to break a covalent bond. I'll just write Be for bond enthalpy. And because it is easier to break the carbon-iodine bond than it is to break the carbon-fluorine bond, because the carbon-iodine bond has the lowest bond enthalpy, it's actually easier to break when it undergoes a nucleophilic substitution reaction. So that means iodoalkanes react faster than fluoroalkanes, So fluoroalkanes take the slowest because they have the strongest bond and the highest bond enthalpy, then chloroalkanes, then bromoalkanes, then iodoalkanes, which have the lowest bond enthalpy. That means it's substituted more easily, the bond is broken more easily because the bond is weaker. Thank you for watching the video. I've zoomed out so that you can look at all of the notes all together, and you can take a screenshot or a picture if you want to. Let me know if there's anything you don't understand or if I didn't explain it well enough in the comments below.